Good morning, everyone. I'm Xiangyu from Tsinghua University. Today, I will present our work on intelligent network on data plane, FENIX, which enabling in-network DNN inference with FPGA-Enhanced Programmable switches. Machine learning has been widely used for network traffic analysis, such as intrusion detection, malware identification, and traffic classification. Traditionally, these machine learning tasks were performed in the control plane. The data plane extracts the traffic features, sends them to the server, and then waits for the inference result. This approach is flexible, but it introduces high interaction latency, often at millisecond level. For time-sensitive tasks, such as detecting malicious flows in real time, this latency is too high. Therefore, recent systems try to move machine learning inference into the data plane. By doing inference closer to the packet path, they can reduce the interaction latency to microsecond level or even lower. However, this shift also introduces new challenges which motivate our work. Although data plane machine learning reduces latency, existing solutions still face fundamental trade-off between three goals: latency, throughput, and accuracy. Control plane approaches can run complex models, so they may achieve high accuracy, but they sacrifice latency. SmartNIC-based systems reduce latency, but their throughput is usually limited to hundreds of Gbps, which is much lower than the multi-terabit throughput of modern switch ASICs. Programmable switch-based systems can process traffic at line rate, but the switch pipeline has limited computation and memory resources. As a result, they usually support only simple models, such as decision trees, random forests, or binarized neural networks, which can hurt accuracy on complex tasks. So the question we ask is, can we achieve all the three goals at the same time: low latency, high throughput, and high accuracy? FENIX is our answer to this question. Our key observation is that switch ASICs and FPGAs has complementary strengths. A programmable switch ASIC is extremely good at line rate packet processing and feature extraction. It can process multi-terabit traffic with deterministic pipeline latency. However, it is not suitable for complex deep neural network computation. On the other hand, the FPGA provides much richer computation resources. It can efficiently support neural network operators such as convolutions and recurrent cells. But its throughput is still much lower. Therefore, FENIX adopts a hybrid architecture. The switch ASIC serves as the data engine, extracting and selecting useful feature vectors from raw traffics. And the FPGA serves as the model engine, executing high-accuracy deep neural network inference. Only a curated feature stream is sent to the FPGA instead of sending all packets. This division allows FENIX to keep line rate packet processing on the switch, while enabling complex deep neural network inference on the FPGA. Now, let's first look at the overall hardware setting. On the left side, we have programmable switch ASIC. It includes a parser, a match action pipeline, SRAM and TCAM, and a deparser. On the right side, we have FPGA coprocessor. It provides more flexible hardware resources for neural network inference, such as LUTs, flip-flops, BRAMs, and DSPs. In our design, the switch ASIC collects features from the traffic and sends them to the FPGA for model inference. The FPGA returns the inference result back to the switch, and the switch applies the corresponding traffic actions. However, making this simple idea work at high speed is not trivial. The key challenge is the throughput mismatch between the switch ASIC and the FPGA. Modern programmable switches can process traffic at multi-terabits per second. In contrast, Even high-end FPGAs typically provide much lower effective processing throughput for deep neural network inference. Therefore, if we simply mirror all packets or all features to the FPGA will quickly become the bottleneck. This would either cause packet jobs, long queues, or unacceptable latency. So the central design or challenge of FENIX is, how can we let the switch process all traffic at line rate, while sending only the right amount of useful feature information to the FPGA? Our solution is a fine-grained feature rate control mechanism implemented in the data engine. FENIX has two main components. The first one is the data engine on the switch ASIC and the model engine on the FPGA. The data engine extracts features and selects which flows to offload. It also uses a probabilistic token bucket to control the feature sending rate. This is important because it bridges the throughput gap. The model engine receives the selected feature vectors and runs deep neural network inference on the FPGA. Together, these two components allow FENIX to extract features at line rate, offload only selected vectors, and make flow-level decisions using the returned results. Now let's focus on the flow tracker in the data engine. It maintains per flow state in a flow info table stored in switch SRAM, indexed by 5 tuple hashes for each incoming packet. The flow tracker first checks whether it is an inference result from the FPGA. If yes, it updates the flow class and drops this internal packet. For normal packets, classified flows are forwarded according to their class. Unclassified flows use a lightweight decision tree for temporary packet-level inference. Meanwhile, the flow tracker updates counters for the rate limiter and buffer manager. FENIX uses a pre-computed probability table to select flows fairly. Then, a token bucket limits the total rate to match the FPGA capacity. For selected flows, the buffer manager packs recent features with the flow ID, so the FPGA receives the compact feature vectors, not raw packets. The model engine runs on the FPGA and performs DNN Inference. When a feature packet arrives, it separates the flow ID from the feature vector. The feature vector is sent to the DNN model, while the flow ID is kept for matching the result. After inference, the result is matched with the flow ID and returned to the switch. The DNN model supports models like CNNs or RNNs with int8 quantization to reduce cost. So, compared with the switch-only designs, FENIX can support more expressive models. Now let's look at the implementation. We implemented FENIX on our own FPGA-Enhanced Programmable switch prototype. This prototype integrates a Tofino 2 switch ASIC and a Xiangsheng ZU19EG FPGA on the same board. The two chips are connected through high-bandwidth on-board channels, allowing us to evaluate the full FENIX pipeline on real hardware. Now let's look at the evaluation. We test FENIX on two tasks. The first one is VPN traffic classification, and the second one is malware identification. Because the data sets are imbalanced, we mainly report micro F1 together with precision and recall. We also compare FENIX with representative baselines, include the control plane baseline, switch-based, and semantic-based inference systems. First, let's look at the accuracy. FENIX performs well on both VPN classification and malware identification, and outperforms most switch-only and semantic-based baselines. The reason is that FENIX can run more expressive deep neural network models on the FPGA, rather than being limited to simple or heavily compressed models in the switch. So the key takeaway is FENIX improves accuracy while keeping feature extraction in the data plane. Next, let's look at latency. Compared with the control plane approach, FENIX greatly reduced both transfer latency and inference latency. Instead of sending features to the CPU, FENIX used direct hardware communication between the switch and the FPGA, avoiding software stack and memory access overheads. As a result, FENIX achieves microsecond-level latency, which is much lower than the control plane baseline. This slide shows the scalability of FENIX and the increasing flow concurrency and throughput. In the hardware testbed, FENIX maintains stable accuracy as the new flow rate increases. For larger scales, we use a simulator calibrated with real hardware results, and the results shows that FENIX can reach TBPS level throughput. The key takeaway is that FENIX does not require the FPGA to process every packet. With probabilistic rate control, it selectively sends useful feature vectors and maintains robust performance even under high traffic load. Finally, we look at hardware resources usage. On the switch ASIC, FENIX uses only a small portion of SRAM and TCAM and occupies a limited number of pipeline stages. So the switch still has room for other packet processing functions. On the FPGA side, both the CNN and the RNN models have moderate resource usage, including LUTs, flip-flops, VRAM, and DSPs. Overall, this result shows that FENIX has reasonable hardware overhead on both the switch and the FPGA, leaving headroom for future optimization of larger models. Now, let's give me a conclusion. FENIX is a hybrid in-network deep neural network inference system that combines programmable switch ASICs and FPGAs. The switch ASIC performs line-rate feature extraction and fine-grained rate control, while the FPGA performs high-accuracy deep neural network inference. With this design, FENIX addresses the throughput mismatch between the two chips and achieves low latency, high throughput, and high accuracy. That's all. Thank you. Any questions?